Hi everyone. This week we will be learning about polynomial functions and an important thing that we an important information that we always are interested in for polynomials, which is called the zero of a polynomial. Now, there are different interpretations of what it means. So first of all, in terms of language, um, zeros of polynomial can also be referred to as roots of polynomial, and they are closely tied with the factors of a polynomial. Okay, how is that? So example, if 2 is a 0, right, then we also say that 2 is a root, and we also say that x minus 2 is a factor. Okay, so what is it really? So it is basically, what is it? It is the input that makes the output 0. Okay, which is basically, so it is the x value that makes f of x equal to 0. Whatever that x value is called the zero of a polynomial, or the root of the polynomial, or another way to say that is that x minus that number is a factor of the polynomial. So let's look at this example here, which we can factor by splitting the middle term. So I want to find out, so find x, so f of x is 0. So what I do is I set this equal to 0. I factor this. So this is why there is a relation between the zeros, the roots, and the factors, because you get the factors or the roots by first factoring the equation. Okay. Now when you have product of two things equals 0, either this is true or this is true. Consequently meaning x is 2 or x is 1. Okay. So these are called the zeros of the polynomial. Now which means if you draw this function, now that's a parabola, what is happening is you're saying that at x equals 1 and at x equals 2, the graph goes through these points. It goes through the x-axis. And this parabola has a positive x square coefficient, so it is upward opening. So these values, these which are these, you can consider them zeros or roots, and these are also the x-intercepts. Okay, so all of these terms can be used interchangeably. X-intercept of a polynomial function is a 0, is the root of the function, and x minus that number is one of the factors of the polynomial. Now our goal this week is to understand the different techniques that can be used for either finding the root or estimating the root. It turns out that while for this case it's easy, you can factor using trinomial factoring, or we can even use quadratic formula, it's not always easy. When we go for higher powers of x, it's not straightforward, which means it is possible that we are not able to find the actual root, in which case we want to know, can we approximate it, or can we find some properties of the root, that's going to be the goal for this week. So we're going to start off by trying to find nice roots. Now what is nice is, nice meaning either integers or rationals. Right? So example like 1, 2, 3, -4, or nice fractions like 1/2, 3/4, 1/3, -2/3, etc. Which means we are trying to first find roots which are not like radicals, right? Root 3 or root 4. But in our definition of nice, these are integers or rationals. So for that, we have this theorem. It's called the rational zero theorem. So here's what it says. This is a standard notation for any polynomial, right? It basically says it's a polynomial of degree n, where these numbers an minus 1, a0, these are just the coefficients. So it says that if this polynomial were to have an integer coefficient, then every rational zero of p is of the form where these numbers are factors of either of the constant term and q is the factor of the leading coefficient. Okay, so it's going to make more sense if once we apply this to this example. So here in this example solution, find the rational zeros of this polynomial. Step 1, we check the coefficients of px are integers. Okay, they are 1, -3, and 2, which is good, right? Because this theorem can only be applied if they have integer coefficients. Okay, step 2, a0, which is the constant, is 2. That's the last number, and an is 1. Okay, step 3, so the roots are p over q, where p divides a0 and q divides 1. If p divides 2, there's only 4 set of possibilities. P can be plus minus 1, or p can be plus minus 2. Because the 4 numbers that divide 2 are 1, -1, 2, and -2. Whereas q can only be plus minus 1. So p over q is either plus minus 1 over plus minus 1 or plus minus 2 over plus minus 1, which is plus minus 1 or plus minus 2. And step 4 is check which of these are the roots. Okay, so what did we do here? The result says that any rational zero of this polynomial is of this form, where the numerator divides this last number and the denominator divides the first number. So we list down all possibilities. All possible ways of a number dividing 2, meaning of things that are factors of 2, are plus minus 1 and plus minus 2. And all numbers dividing 1 or factors of 1, the only factors of 1 are plus minus 1. So once we have these possibilities for numerator and denominator, the fractions that can be formed are either plus minus 1 or plus minus 2. And then to check, we just plug in. So p of 1 is 1 cubed minus 3 times 1 plus 2, which is 3 minus 3 is 0. So 1 is a 0. Negative 1 is negative 1 cubed minus 3 times negative 1 plus 2. That's negative 1 plus 3 plus 2, which is 4, which is not 0. So it's not a factor. 2 is 2 cubed minus 3 times 2 plus 2, which is 8 minus 6 plus 2, which is not a factor. Negative 2 is negative 2 cubed minus 3 times negative 2 plus 2, negative 8 plus 6 plus 2, which is 0. Well, I said the previous one is 10 minus 6, 4, which is. So what are the zeros? The zeros are 1 and negative 2 are the zeros. Okay, so there's 4 distinct steps here. The first 2 are just setting things up. So the first one checks that the coefficients are indeed integers. The second one lists down, the number that the numerator is going to divide and the number that the denominator is going to divide. Right? And so the next step, you look at all the possibilities. The possibilities are plus minus 1, plus minus 2, plus minus 1 for denominator. Therefore, the division of these, the possible values are plus minus 1 and plus minus 2. And the last step is always to check Now, it's not necessary that all of these numbers that you found are actually the zeros, right? Maybe sometimes all of them come out to be zeros, but most often not all of them is going to come out to be zero. So one way to check that is to plug it in, right? And use the definition that what is a zero? It's an input that makes the function zero. So when you plug it in, if it does make the function zero, then that's good, because that means you're done. But if it does not make the function zero, then you have to ignore that. Yeah, that particular number is not going to be a zero. Now, in the next example, in the next video, we are going to do another example where these are going to remain the same, but for step 4 to check, we will use something that we have learned before, which is synthetic division. And the reason is, sometimes when you have higher powers, plugging in each number is difficult. You have to do a lot of calculation. Whereas doing the synthetic division and using the remainder theorem is going to be way quicker. Okay, that's it for this video. Thank you.